In this next video, we'll be looking at how X-rays work. So what is an X-ray? An X-ray is a type of electromagnetic radiation. They have incredibly high frequency of around, say, 10 to the 16, 10 to the 20 Hertz. They also have very short wavelength. So an X-ray is formed when an electron, which has an incredibly high kinetic energy, is rapidly stopped. When this electron is rapidly stopped from its high kinetic energy state, it produces electromagnetic radiation in the form of X-rays and heat. So how does an X-ray machine work? Well, if we get the diagram up here. So in this diagram, you can see that we have a low voltage source. So this is around 6 volts. So this low voltage source heats up the filament. So the filament is where the electrons come from, so it's the cathode. So the filament. So the filament is getting heated, and when it's heated, it releases electrons. So in this circuit, we have a high potential difference of around 10,000 to 50,000 volts. So this high potential difference accelerates the electrons across the gap, so giving it high kinetic energy. When the electrons have a high kinetic energy, they then hit the tungsten filament, the tungsten anode. The tungsten anode is connected to copper. Copper is a good conductor of electricity and conductor of heat. So copper is used to remove the heat away. We want this heat to disappear, and the way we dissipate this heat is using fins or some form of liquid cooling system. So, in an X-ray machine, a low voltage source heats up a filament, and when this filament is heated, electrons are released across a high potential difference of about 10 to 50,000 volts. These electrons then hit the tungsten anode. The tungsten anode then has the X-ray beam being generated and moved to wherever it needs to go, but the heat that's left over from this transfer of energy is cooled into the copper. The copper then transfers it to the cooling system, which could be fins or it could be liquid, where it cools it down, because 99% of the kinetic energy is transferred into heat and only 1% is transferred into X-rays. So, when the electrons hit the tungsten anode, the X-ray beams are directed to whatever angle the tungsten anode is pointing, based on the conservation of momentum and things like that. So this is an X-ray machine. X-rays produced have a range of frequencies, up until a maximum. These range of frequencies change with the changing of the potential difference. If we increase the potential difference, we increase the intensity of the electromagnetic wave, so the X-ray being produced. So we can graph this. On this graph, we have different potential differences, so different voltages, and the different frequency ranges that they produce. Each of these have a distinctive curve. So you can see that these curves end at some maximum. They have a maximum frequency. The intensity increases as the voltage increases. Also, we have a certain spike in the same frequency for each of these different graphs that we have of the frequencies for different voltages. These spikes are characteristic of what the anode is made out of. If we have a tungsten anode, we're going to have a frequency being produced at one wavelength. But if we had a molybdenum anode, the frequency of this peak is going to be a different spot. So, X-rays have a intensity versus frequency graph that looks like this. You need to know how to draw this, and you need to know the main features of it. So we have a range of frequencies that end at a maximum. We have a point of intensity wherever we have the characteristic frequency for our anode, and we increase in intensity as we increase in the voltage. So why do we have a range of frequencies? This is all due to how we actually create our electromagnetic wave. So, if I have a diagram up, what this diagram is showing is electrons going into the atomic size material of the tungsten or molybdenum, or depending on what sort of anode it is. So you can see the nucleus or nuclei of each of the atoms that make up our anode. We can see the electrons passing near these nuclei. So, from chemistry, we know that the nucleus of atoms is made up of protons and neutrons. So, all of these nuclei are going to have a positive charge. Electrons have a negative charge. We know from electrostatics that positive and negative attract. So, as these high kinetic energy electrons go past a positive nuclei, it's going to curve the path, change the velocity of our electron. This change in velocity produces our electromagnetic wave. It produces our photon, which is our X-ray. Okay. If we have a electron that goes directly into a nucleus, it's producing its maximum frequency. It can't get any closer to the nucleus than what it already has. It's smashed into it. So that's going to be our maximum photon that's going to be created. If we have an electron that somehow manages to find a path that goes in between all of these nuclei and it's only deflected slightly, it's going to produce a low frequency or lower frequency photon. If we have an electron that goes near a nucleus and it curves its path, changing the velocity, it produces say a mid-range for an X-ray photon. So you can see this is how we produce a range of frequencies. So this is what was seen from the graph. The relationship between frequency and potential difference has a directly proportional relationship. How do we know this? We need to derive the equation. So, we start off by working out what the kinetic energy of our electrons are that we're firing at our anode. So, the kinetic energy of these electrons is going to be K is equal to E delta V. So the kinetic energy is equal to the electron voltage times by the potential difference. We know from the conservation of energy that if our electron is stopped by the nucleus, and we're going to have the energy of this electron transferred into the nucleus and also into the produced photon. So the energy of the photon is going to be equal to the kinetic energy of the electron. So the kinetic energy of the electron, K is equal to EV, this is going to have the same energy of our produced photon. The photon will have an energy equal to EV. We know that the energy of a photon is equal to HF. So, if we substitute in for our E is equal to EV and change this capital E into HF, we get that HF is equal to little ev. We can then rearrange this to get F by itself, the frequency. So Planck's constant, our H, is going to go underneath the equation. We're going to be left with F is equal to little e delta V all divided by H. So the frequency is equal to the electron voltage times by the potential difference divided by Planck's constant. So this is how we derive this formula. You need to know how to do this. So the key points from this video. X-rays are produced when an electron with high kinetic energy is forced to slow down or come to a stop. So as it hits this object and comes to a stop, the kinetic energy is lost and transferred into a photon. This photon is an X-ray. So an X-ray tube has the following features. It has a low voltage supply which heats up a filament. The filament is our cathode. In this filament we have electrons. As it is heated, the electrons are released from this filament. A high potential difference can be from 10,000 to 200,000 volts. Accelerates these electrons, creates a very high kinetic energy for the target anode. The target anode is a piece of tungsten normally. It can be molybdenum as well. So the target anode is connected to or attached to a piece of copper. The copper transfers the heat away from this tungsten filament or tungsten anode to a cooling system. This is because 99% of the energy that's transferred into the tungsten and then to copper, because it's attached, is heat. Only 1% of the energy from the electron is transferred into creating an X-ray. The graph of a X-ray, so the graph of intensity versus frequency, produces a range of intensity and range of frequencies due to different voltages. If we increase the voltage, we increase the intensity of our frequencies, but we still get a range. We get a range because as the electrons are passing into the anode, it's the nuclei of the atoms of this anode that cause the electrons to deflect. This deflection creates the photons, which are the X-rays. The differences in the frequencies are due to the gaps in these nuclei. If the electron goes straight through, doesn't actually hit a nuclei, and it's slightly deflected, we get a low frequency photon being produced. If we get an electron that hits a nucleus, we get a maximum frequency. The different anode materials create a different spike at different frequencies. This spike is going to be the same frequency for the same material, but it changes if we change the material. We need to know how to derive the formula. F is equal to little e delta V on H. So this was shown in the video. Need to recap on that and know how to do it. We also need to know how to use this formula. So you can see that in the LiveScribe PDFs. So, key points. So the key points. We have that an X-ray is a high energy photon produced by the slowing down of electrons. We have that the X-ray tube is made up of many different parts. These are the low voltage supply which heats up the filament. This filament allows electrons to move across to our anode. The anode is made out of tungsten and copper. There needs to be a cooling system on this because there's a lot of heat produced. We also need to know how to draw the graph. The graph has characteristics which are, as we increase the voltage, we increase the intensity. We have certain spikes of intensity depending on our anode material, and we have a range of frequencies that end with a maximum. The maximum frequencies and the range of frequencies are due to the interactions between the electrons and the nucleus or the nuclei of the anode material. And we need to know how to derive the formula and use it. So that is X-rays.